Right, we're going to work through many examples of the chain rule now. So in the last video, I talked through the idea of the chain rule, really tried to get at the intuition of it. In this video, we're going to go more through symbolic manipulations about actually using the chain rule to calculate derivatives. There is a difference between the two. There's the intuitive understanding of it, and then there's putting it into practice. It's possible to have either one without the other, so you can understand the chain rule on a theoretical basis without really having much practice computing derivatives, and vice versa. You can apply the chain rule and know all the symbolic manipulations to do that, to do homework problems and exam problems, and have no idea really what the chain rule is actually saying. So in the previous video, we went over what is the chain rule actually saying. In this video, we're going to use it to calculate some derivatives. So the chain rule provides us with a way of calculating the derivative of a composition of functions. And the precise statement I'm going to give right now, I'm not going to go over the proof. It's in the textbook if you want to read it. It just involves some technicalities it's not worth going into in a class at this level. But here's the statement of the chain rule. So our hypotheses, we're going to say, let G be differentiable at A. In other words, G is a function and its derivative exists at A. And let F be a differentiable function at G of A. Okay, so G is going to be like our first function, F is like our second function, or if you're familiar with the outer function, inner function terminology, G is our inner function, F is our outer function. So we're saying G prime of A exists, G is differentiable at A, but also F prime of G of A exists, F is differentiable at G of A. Then what the chain rule says is it says that the composition function, the composite function, which I'll call, let's say, big F, which is F, little f composed with G, is itself differentiable at A. And furthermore, there's a nice formula for the derivative of big F, the composition, at A. And it says that F prime, big F prime, at A is little f prime at G of A times G prime of A. Okay, that's the big statement there. So in other words, if I were to put in the actual composition here, it says that F composed with G prime evaluated at A is equal to F prime of G of A times G prime of A. So it says to find the derivative of a composition, you take the derivative of the outer function, evaluated at the output of the inner function. So not evaluated at A, but evaluated at the output of the inner function, and then multiply that by the derivative of the inner function at A. Okay. Symbolically, this is why I went over the main idea in the last video, is if you don't have that main idea in your head to orient you, this can be very confusing on a symbolic level. It just looks, like there's a bunch of functions roaming around and there's these primes. But if you remember what it said there, it's really just saying that we're multiplying two rates of change, two instantaneous rates of change, to get the overall rate of change on the left-hand side. All right, so now that we have the statement of this, let's first go over the different steps we're going to have to go through to use the chain rule. And then we're going to go through many different examples. I think I have 10 of them that we're going to go over in this video. So I'm going to go through the list of steps here that you need to go through to use the chain rule. And one thing to keep in mind here is these are the steps that you really should go through when you're first learning it. because when you're first doing it, you need to make sure that you're getting all the steps right. You need to make sure your thinking is clear. But what you'll find, maybe not this week or, a week after, or maybe not even till maybe the end of the class, but you should find sooner than later that you should start to try and go through this process without explicitly writing out the substitution, without explicitly writing out u. For right now, I'm going to do it for the first few problems, just to make it super clear what's going on. But by the time you get to even second semester calculus, when you're doing derivatives in Calc 2, you should be beyond writing the u out every time. You should be going just straight to, the outer function evaluated derivative at the inner times the inner, prime. So here's the steps that we're going to go through. So we're going to identify an outer function, f, the inner function g of x. So you have to figure out what's your outer and inner function. You're going to write down the substitution. So we're going to let u be the inner function. This is really just a kind of a notational thing so that we can keep track of what's going on. Express f of g of x as f of u. Okay, and then write the chain rule in the Leibniz notation. So in Leibniz notation, the chain rule says df by dx is df by du times du by dx. That's what I was talking about in the last video about the apples. 3 times as fast times 2 times as fast makes 6 times as fast overall. But now we're actually going to calculate these symbolically. So we're going to differentiate f with respect to u, because we've written f as a function of u. Then we're going to differentiate u with respect to x, because we've written u as a function of x. Then, after we've done those two derivatives, we're going to replace u with the original g of x, which was a function of x that we had before. And then finally, if the inner function is itself a composition of simpler functions, then repeatedly applying the chain rule again. So we'll get to a few of these at the end. At the beginning, we'll just do chain rule once. But there are some times when you have to use the chain rule twice or 3 times, or sometimes even more. So you have to use it as many times as necessary until you reach the basic function on the inside. This is why I'm going to go back up here and give you this quote. So this is a very old saying in math. I have no idea who came up with it. Probably doesn't even matter at this point. But using the chain rule is like peeling an onion. You have to deal with each layer at a time, and if it's too big, you'll start to cry. So I'll just leave it at that. But it is like peeling an onion. You're peeling away the layers. There's all these outer functions. If you have multiple functions, there's outer function you keep having to peel until you get to finally the innermost function, at which point you're done. And as I said a moment ago, the more and more comfortable you get with this, you should be able to do this without explicitly writing out the u equals g of x substitution. It takes a bit of practice, so don't be discouraged at first if you need to write it out. It's really more important when you're first learning this that you take your time, understand the procedure correctly, and if you focus on that, you'll find that your speed will naturally increase on using the chain rule, until eventually you'll just be able to do it without writing out the substitution. Okay, so let's just jump right into it. Find the derivatives of the following functions. So y is equal to sine of 7x minus 2. So this is a composition of functions. It's the function 7x minus 2 followed by the sine function. So the sine function here is what we would call the outer function. 7x minus 2 is the inner function. And so since 7x minus 2 is the inner function, I'm going to go ahead and write u is equal to 7x minus 2. Then what I have is I have y of u is equal to sine of u. Because remember, this is saying y of x. This is saying y of x is equal to sine of 7x minus 2. But if 7x minus 2 is u, then really y is just sine of u. And u of x is 7x minus 2. Okay, so this is the dependence. We've introduced this u that's kind of standing. It's almost like it's somebody that's coming between two people. It's coming in between y and x and saying, nope, I'm going to be the intermediary that the interface between u2. So what we need to do is find, so we need to find dy dx. So the chain rule says this is dy du times du dx. Okay, well, what's dy du? Well, we have y as sine u, so dy du is derivative of sine, which is cosine. What's cosine u? And then we're going to multiply that by du dx, the derivative of 7x minus 2, with respect to x is 7. So now we're at the point where we've calculated the two derivatives, but we still have the dy du in terms of u. So the last step then is to go and take the 7x minus 2 and put that back in. And then I'm going to write the 7 out in front because it's a constant, and I get 7 times cosine of 7x minus 2. So that's the derivative, 7 times cosine 7x minus 2. Okay, moving on. Number 2. F of x is equal to x to the 6th minus 5x plus 1 all to the 13th. All right. So one thing to mention here before we get into this is, in principle, I don't need the chain rule here. If I really wanted to be, if I really wanted to put myself in pain, I could decide to multiply this all out. So I could just keep multiplying out until I eventually got this enormous, what would it be, 78th degree polynomial, x to the 78th plus whatever to the 77th, and so on. Now, there's two reasons we don't want to do this, right? First of all, it's a pain, and it's unnecessary. But another reason is, if we did it term by term that way, after we differentiated, we just have another big polynomial. And we wouldn't really be able to get any insight into the nature of the derivative by looking at that big thing. In fact, by using the chain rule and being able to kind of preserve these factors, we're going to be able to see a lot more information about the derivative than we would if we had just multiplied everything out. So, of course, it's much better here to use the chain rule. So our outer function here, think about what's going first and then what comes second. The outer function is raising to the 13th power because we do that last. The polynomial is first. So our u here is x to the 6th minus 5x plus 1. And our f of u then is u to the 13th. And we want to find df dx, which is df by du, times du by dx. So df by du is the derivative of f with respect to u. So f of u is u to the 13th. So that's going to be 13 u to the 12th. And then we're going to multiply that by du dx, derivative of u with respect to x, which is 6x to the 5th minus 5. And lastly, then I need to go and take my u, which is the whole trinomial here, and substitute that back in for my u here. So it's going to be 13 x to the 6th minus 5x plus 1, all raised to the 12th, times, now this is how we, colloquially, this is how we say it, times the derivative of what's inside. So the derivative of what's inside is 6x to the 5th minus 5. So that's our derivative here. All right, the next two kind of go together, and there's a point to them. So I'm going to bring number 3 and 4, and I'm going to put them up here, and I want you to go ahead and pause the video and take time, however long you need, 5 minutes, however long, and try and do both of them and see how you compare your answers with them. So bring them up here. So here they are, 3 and 4. So go ahead, pause the video, do number 3 and number 4 together, and then we'll go over them in just a minute. All right, so you should have gotten two different answers here. And the difference between these two, it's the same two functions, but they're done in opposite orders. So in one of them, you do the cubing first and then the cosine. The other one, you do the cosine and then the cubing. And so this will really illustrate, if you're not clear about the inner and the outer function, this is really going to illustrate the difference between that. So on this cosine of t cubed, we're doing the cube first and then the cosine. The cubing is the inside function. So that's our u. U is equal to t cubed. And then y of u is equal to cosine u. So dy dt here is dy by du times du by dt. Derivative of y with respect to u is minus sine u times derivative of u with respect to t, 3t squared. And we substitute back, so we get minus sine of t cubed times 3t squared, and we probably write this not quite the same, so we probably write this as minus 3t squared sine of t cubed. That would be the usual way to write this. Now let's compare that to number 4. Number 4 is very different. Here, the cosine is the inner function. Remember, cosine cubed, this is really saying cosine of t, bracket, all cubed. It's saying do the cosine first and then cubed. So cubing is the outer function here, not the inner. So we're going to let u equal cosine t, and then y of u is actually u cubed. So we still have dy dt is dy du, du dt, except the derivative of y with respect to u now is 3u squared. And then we're going to multiply that by derivative of u with respect to t, which is minus sine t. So notice the difference here. We're not going to get the same derivative at all. It's not the same. 3, so u is cosine, so 3 cosine squared times minus sine. So altogether here we get minus 3 cosine squared t sine t. So if you compare those, I'll move them up here so you can see them. So compare those. Those are different functions. They're not the same at all. So it definitely makes a difference that you're keeping straight what is the inner and the outer function. All right, let's do number 5. So this is square root of x squared plus 9. So the key here is in order to use the square root for the derivative, you need to write it as a fractional power. So if you want to take another minute, pause the video, see if you can work this one out using that approach. Okay, so first let's start here by writing g of x. We'll just write this as x squared plus 9, all raised to the 1/2. And now what we're going to do is say our inner function is the x squared plus 9, so that's going to be u. And g of u is then the square root function. So we're doing the polynomial first and then raising it to the 1/2 power, taking the square root. The derivative of g with respect to u is 1/2 u to the minus 1/2. Remember, the power rule also applies for fractions. So that's 1/2 u to the minus 1/2 times du dx, which is 2x. Now, to really express this, not only should I plug back in the x squared plus 9 here for u, right there, but I should also take the exponent and make it look more like the original function. So the minus, I should put it in the bottom. The 1/2 I should convert back to a square root. Again, you don't have to do this, but it's just kind of nice. Also, notice the 1/2 and 2 cancel. So what I end up with here is a 1 over square root of x squared plus 9, but I still have an x on top. So I've got x over square root x squared plus 9. So that is the derivative here. Okay, well, we've got 5 more. We're halfway done, but they're going to start getting a little harder. So let's look at number 6. Okay, so this is y of x is x minus 2 all over x plus 1. So it's a rational function raised to a power. So it's cubed. So again, if you want to pause the video, see if you can work through this. And maybe if you're feeling super confident, see if you can do this without using u. So without writing it out explicitly. If you need to, that's fine. But see if you can at first. All right, let's go through this. I'm going to do this without writing out u. So see if you can follow along. Even if you needed to use u, I'll give you an example of what it looks like when you don't write it out. So the way that we would write this out is dy dx is equal to, okay, so what I'm going to do is realize, okay, my adder function is the cubing. So that means I just pretend that everything inside here in parentheses is just a blob. So that's my u. So I'm just focusing on the cube function. So I just say the derivative of cubing is 3 times whatever squared. So it's 3 times all this stuff in here squared. Now, that's just the outer function. Now that I've done this, I have to multiply by the inner function, the derivative of the inner function, which I need to use the quotient rule. So this one is the chain rule, and then the quotient rule is inside of it. So the quotient rule I have to remember is low d high, derivative denominator, denominator times the derivative of the numerator, which is 1, minus numerator, derivative of the denominator, also 1, all over denominator squared. All right. Now it's a matter of cleaning it up. All right, so what do I have here on top? I've got an x plus 1 minus x plus 2. Okay, so that's nice. The x's are going to go away. And, okay, so I'm going to have 3 times 3, so I'm going to have a 9. And the rest of it, I just need to gather the common factors together. So altogether, it looks like I've got 3 times 3, that makes 9. There's 2 factors of x minus 2 on top, so 9x minus 2 squared. Over, now after distributing the 2, there's 2 factors of x plus 1 on the bottom here. And then there's also 2 factors out here from the quotient rule. So those all together make x plus 1 all to the 4th. So 9 times x minus 2 squared all over x plus 1 to the 4th. So hopefully that gave you an idea of, what it would look like once you're more familiar with this, when you're just writing it up straight from start to finish, quickly bypassing writing out the substitution. Now, in the next one, number 7, so for number 7, there's a couple things that are different here. The main thing is I threw in a couple constants here. So I threw in a and b. So you're going to have to do everything in terms of a and b. But also, I made it a function of u. So that kind of throws off our usual symbols. We're generally using u as our intermediate variable. So if you still want to use u, you just have to call it something else. So what could we call it here? Well, first of all, before we get to that, let's realize that this is a product. So the main thing we're using here is the product rule. So that means, I'm going to switch to the prime notation here. W prime of u is going to be the first, the derivative of the second, plus the second, the derivative of the first. So this times okay. Now, actually, I don't think we need to write out the substitution for each of these because the inner function here is just a constant multiple of u. And this happens really often. If you have just a linear inner function, then all you do is you just pick up the factor. So what that means is I'm going to get e to the au. The derivative of the sign here is going to be cosine, but because there's a b, I just pick up a factor of b, because the derivative of bu is b, just like the derivative of 3u would be 3. So I get b times cosine bu plus, and now I've got, let me switch the order of these. So the derivative of e to the au, I'm going to pick up a factor of a, so plus a e to the au times sine of bu. And what do I have all together? Well, I should factor out e to the au. And what's left is, let's see. Let me put the sign first. It looks more natural. I've got an a sine of bu plus b cosine bu. And that's the derivative. So a couple things to notice here. I started with an exponential times a sine, and I ended up with what's essentially a linear combination of an exponential times a sine and an exponential times a cosine. So that's just something to observe, that when we start with functions that are combinations of exponential and trig functions, and we differentiate them, we stay within combinations of exponential and trig functions, but we may get a different combination of them. All right, moving on to number 8. So this type of problem is one that I've put on exams before, and it tends to trip people up. So, and I think it's because people get kind of lost in the algebra. So we want to find df dx. So first thing to notice here is it's a product rule. So we need first derivative of the second. Okay, so let's see, what's the first? Well, it's just 6x squared plus 5 all cubed. Right, that whole thing is the first. Then we're going to multiply this by the derivative of x cubed minus 7 to the 4th. And then we're going to add to that. Now normally, when I do this, I do first derivative of the second plus second derivative of the first. I'm going to do first derivative of the second plus derivative of the first. So I'm going to keep the same order. And then times the second. Okay, so what's going on here? So the point is, when we're differentiating these, we're going to lose a power here, but we're also going to pick up something from the chain rule. But there's going to be enough common factors that we'll be able to factor stuff out. So let me show you what I mean. We've got this times, now what is the derivative here? So now is when we have to use the chain rule. So notice we're using the product rule, but then the chain rule twice on each term. So the chain rule applied to this says it's 4 times x cubed minus 7 all to the 6th. Sorry, x cubed minus 7 all cubed. I don't know how I came up with 6. I think I dropped the 7. So my mind, I dropped the power of 7, except it's not a power, it was a term. So cubed times the derivative of what's inside, which is 3x squared. Okay, so power rule, derivative of what's inside, plus, now I'm going to differentiate this, which has derivative 3 times what's inside squared, the power rule, times the derivative of what's inside, 12x. And then this just tags along, x cubed minus 7 to the 4th. Okay, now this is kind of a mess. What can we do with it? Well, what we need to realize is if we take the smallest power of each of these, so if we look at this, 6x squared plus 5 all squared, and then if we look at x cubed minus 7 all cubed, those are the smallest power of each of those. So we can take out a GCF there. Now, is there anything else we can take out? Well, actually there is, right? There's an x there, and there's also an x over here, and there's a factor of 12, and there's a factor of 12 there. So actually, there's quite a bit we can factor out, and this is what trips people up. I think it's the algebra, figuring out what exactly we're factoring out and what's left over. So what we're factoring out is we're going to factor out a 12x times a 6x squared plus 5 squared times an x cubed minus 7 cubed. And then we're left over with a bunch of stuff. So we have to figure out from each term what's left over. So let's see, from this first one, we have one factor of 6x squared plus 5 that's left, because this was we only took out the squared, and that's cubed. But there's also, because this only has 12x squared, there's also another factor of x there. Right, so this makes 12, if I distribute this through, 12x squared, which is what we have here. And then we've got the right power, so we got the power up to 3 there. And then we have this power we already factored out. So that's what's left over from the first. Now we have to add what's left over from the second. Okay, so there's 12x. There's the 6x squared plus 5 squared. And then there's everything except one factor, right? We have to have an extra factor of this to make it to the 4th. So we got plus 3 times x cubed minus 7, a single factor of x cubed minus 7. Now we need to clean up what's in here. So we're going to distribute 6x cubed plus 5x. And then here we got plus 3x cubed minus 21. Okay. So the 6x cubed and 3x cubed, I can combine those. That makes a 9x cubed. And now I think I'm about ready to be done here. I've got 12x, 6x squared plus 5, all squared, x cubed minus 7, all cubed, times a 9x cubed plus 5x minus 21. Okay, so are you ready for the last two? These are the hardest. And the reason is we're going to be using the chain rule repeatedly. So we're going to have to peel back layers of the onion. So try not to cry. Let's go on to number 9. All right, so y is tangent squared of the secant of the cosine of 4x. There's many uses of the chain rule here. There's lots of layers of the onion you have to peel back. So if you're feeling up for a challenge and you're feeling confident, go ahead, pause the video, see if you can do this. If you're not feeling up to it, or you just want to see this worked out, then you don't have to pause the video, but I'll return and do this in just a second. Okay, so we're going to find dy dx here. All right, so I'm going to do this without using any substitutions, because if I wrote out every substitution, it would take up like an entire page. So our outer function here is tangent squared. So actually, let's count how many functions there are here. There's 4x, that's 1. Then there's a cosine, 2. Secant is 3. Tangent is 4. Squared is 5. So this is a composition of 5 different functions, which means we're going to have to use the chain rule 4 times. There's 4 layers to peel back. So the first one is, actually, let me rewrite this. It's because that power is kind of visually doesn't make it clear. So this is really what's going on. That square, the 2 is really on the outside there, because it's all of this stuff squared. So what we're going to get is 2 times the tangent of the secant of the cosine of 4x. Okay, so now we've done it once. So we peeled back 1 layer. Now we have to go back. So now we need to ask, okay, what's the derivative of this thing inside brackets, which is the tangent of the secant of the cosine of 4x? So that's going to get multiplied by, now the derivative of tangent is secant squared. So we're going to get secant squared of the secant of the cosine of 4x. And we've peeled back another layer. Okay, so you start to see the pattern here. Every time you're taking the derivative of the next layer, but you leave the inner function the same. You don't change it. You evaluate it at that inner function, whatever that inner function happens to be at that stage. Okay, we still have to multiply again. Keep multiplying. But now we're finding the derivative of this stuff. Okay, so secant of cosine of 4x. Derivative of secant is secant times tangent. So we get secant of cosine of 4x times the tangent of cosine of 4x, right? So that's not, there's not 2 factors here because I did the chain rule twice. It's just because the derivative of secant is itself a product of 2 things. It's secant times tangent. Okay, we're still not done. Now we're looking at cosine of 4x. The derivative of cosine of 4x would be minus sine of 4x, because the derivative of cosine is minus sine. And then finally, now we're peeled back all the way to the last layer, 4x. So we're just left with a factor of 4. If we put this all together, it's kind of a mess, but let's see. We've got a 2, we've got a 4, we've got a minus. So altogether there's a minus 8. So it's minus 8 tangent of secant of cosine 4x times secant squared of the secant of the cosine of 4x times the secant of the cosine of 4x times the tangent of the cosine of 4x times the sine of 4x. That is the derivative, believe it or not. So the point of this problem is, it's not like you're really going to see a function like this probably in anything in the real world, but it's to stretch your muscles, to really stretch your chain rule muscles, so that if you can follow the intricacies, the different layers involved here, then you really know that you've got a handle on the chain rule. So if you got a little lost in here, don't worry. It's easy to get lost the first time, but this gives you an idea when you're taking composition of a composition of a composition, how you repeatedly apply the chain rule. Let's do one more. This is number 10. So this is also one of these ones we're repeatedly applying the chain rule, although this one I don't think it is quite as many times, but maybe about as confusing because it's the same function that's getting, the same type of function is getting composed over and over. So if you're up to the challenge, pause the video, try this out. If not, just wait a second and I'll go through calculating this derivative. Okay, so congratulations if you think you got this. Let's go and check to see if you were right. So the first thing I'm going to do is, just to ease my mind, I don't want the square roots. I'm going to write these all as 1/2 power. So I'm going to say this is x plus x plus x to the 1/2 all to the 1/2 all to the 1/2. So let me make sure I got that right. So we got square root of x plus the square root of x plus square root x. Yeah. So I just converted all the square roots to 1/2 powers. So let's see what the derivative is here. So it's going to be 1/2. Going to come all the way out in front. So 1/2 x plus x to the 1/2 to the 1/2. All of this to the minus 1/2. Now I have to differentiate what's inside times the derivative of what's inside, which is going to be 1, because that's the derivative of x, plus 1/2 x plus x to the 1/2 all to the minus 1/2 times the derivative of what's inside here. Okay, so now I'm starting to get a little bit, I wish that I had more room on the end of the board here. So 1 plus 1/2, all this to the minus 1/2, times the derivative of what's inside, which is 1 plus 1/2 x to the minus 1/2. Okay, let's see if we can clean this up. What I'm going to try and do is convert some of these 1/2 powers back to square roots. So we've got 1/2. Now this is minus 1/2, so that's going to be 1 over the square root of x plus the square root of x plus square root x. Okay, everybody with me so far? So this is this. This is this. What else is left? Now we've got 1 plus, this is going to be 1/2 times 1 over square root of x plus square root x times, in parentheses, 1 plus 1 over 2 square root x. Parentheses, brackets, and I do believe that that is correct. Let's see. Yeah, I think this is it. Is there anything else we could do? Let's see. I mean, I guess we could distribute this stuff across here. Let's see what that does. So we got 1 plus. So if I distribute across the 1, this is going to be 1 over 2 square root x plus square root x. And then I distribute across the 1 over 2 square root x, that's going to be plus another 1/4. Now the two square roots would actually combine here and give me a square root of x squared plus x to the 3/2. And, you know, this is about as far as I feel like taking it. We could keep going by getting, you know, all sorts of common denominators and stuff like that, but this is a pretty good form right now. So this is probably the most confusing, I think, of all of them. I've seen this in calculus textbooks before. One of the nastiest ones probably in any book. So Hope you enjoyed this video about finding derivatives using the chain rule. In the next video for my class, we're going to go on and talk about derivatives of other exponential functions. We know how to differentiate e to the x, but we can use the chain rule to figure out the derivative of a to the x exponential function with any base a.